Okay, so last time just started Unit 3 with an introduction to Unix and Git and some tools stuff. Hopefully that was useful. If you, I don't know, I'll take a vote actually from people who are here. Do you want more or less of that and move on to the algorithmic stuff? I'll leave it to everyone. Yeah. Do you want a bit more on, I'll talk a bit about software licensing now because that's probably useful for when you go get a job, but I won't. If you want more Git demos or stuff, maybe I can sneak that in at the end. Just give me a heads up. Like, I think all the tutorials are this week, so if you need a bit more help from me, but getting in there and doing it and trying to break stuff is the way to do it. So maybe we'll go for that way. Okay. So yeah, we get 3 more hours of Unit 3 and then 3 more hours and I'm done. So you're through my bit. So be a bit quick through Unit 3. So I got to keep an eye on that. Okay. So we'll jump down. Git and Unix and stuff. Yeah, I guess big bit of advice when you're going this stuff is like Git's one of these ones where you're going to get the first experience of banging your head against the wall and computer telling you you're wrong constantly. Trick's not to get downhearted or feel silly. Like everybody does that. It's like my whole day today at work was doing that. So just in a different context. So that's pretty normal. I didn't talk too much. Yeah, just keep trying. This is basically like that XACD comic. It's like you can't go too wrong. It's like if you have the remote, your local one gets in a really bad state, you can just delete it and find it again. Like you can copy the files you were doing somewhere else. If everything goes really wrong, there is always the nuclear option of restarting. So you can't, it is keeping track of everything though. It's very hard unless you're force pushing. So I didn't give you that instruction, but syncing with the remote, you're going to pull to get the remote changes and push to push your local ones back up. If you force push, that's when things will go wrong. Force push to main is where you do the big problem. So be careful before you do that. That would be my advice. I had an intern at a place I used to work and they force pushed away all of our repo. But we had a local copy each, the other people who were working there, so we could, the one back in GitHub, we could back from our local copies. So that's one of these advantages of having it distributed. That's not so obvious when you're beginning. Yeah, that's actually a permissions problem. So whoever set up the security at that place was the person who should have gotten in trouble, not the intern. So, okay. That's the idea of source control. Talked a little bit about IDEs. Basically, it's a text editor with some extra stuff. I don't think there's much more to say about that. One for you guys, I was sneakily using it in VS Code. I didn't really talk about it, but the GitHub integration will help you out. That's this little one over here. So let's try actually opening a repo. I'll open here. This is a Git repo at the base, so you'll get all the track changes stuff happening. So once it's caught up. So you notice I've got changes here. All these things I was doing by the command line last time, there'll be automation in the code editor. So that's mostly happening over here. So if I click on this guy, I can see changes. So this is basically Git status on that side running there. And you can see if I click on this, it'll go, okay, looks like you've gone through here and you've renamed n samples to num samples everywhere. If I want to do the commit message, like yesterday I was getting stuck in Nano, I can just do changed variable name, blah, commit, and then you can sync remotely, which is the equivalent of git push. I can do all that stuff. You can do it from the editor. It's good to learn the magic spells on the command line though, so you feel like a real programmer. There's no other reason. Again, you can do it all in GitHub as well. Like you don't actually need a local editor. You can do it all there. Any questions on that? That's all I think I missed that I wanted to say last time. You will get like a really good one will have a debugger. The state of the Julia debugger is kind of trash at the moment. If you're working in another language, that'll be better. I think going forward with Julia, that will be a lot better. If you've got really fancy ones, you'll get code completion. Anyone using Copilot? Anyone brave and embracing the future? No, LLM embedded in your thing, it will autocomplete for you. Interestingly enough though, and this goes into the next bit, if you start typing the inverse square root algorithm, it will autocomplete that, the same as what I showed you in C. So one of these things of LLMs is like, it's not so much LLMs, it's actually common to neural networks, is you can have a thing called mode collapse, where it just regurgitates the training data perfectly. And that's kind of complicated because I don't know if you remember, I said I said it out offhand and maybe you didn't pick up on it, but I said that was released as GPL, the Quake 2 inverse square root algorithm. So that's actually protected and it's in the training data and it got regurgitated back. So you're actually using something that somebody else wrote and they have restrictions about how you should be using that intended legally. So if you go and use that in a commercial context, there could be bad things happening. So in an educational context, knock yourself out, use all of the LLMs you want, like help you out, help yourself out, but be careful, like, because it will just regurgitate and it's a gray legal area, like completely gray to me. I don't know, maybe you guys have an opinion about it, but like if you're using open source stuff for training, should the model be open? I don't know. I don't actually know. It's complicated, especially when you're in a commercial environment. You can do all sorts of cool things, like most code editors will support a bunch of stuff. Like if I go forgotten VS Code already. You get some magic tricks, like if I hold Alt, I can do block, block, block. So if you're trying to do boilerplate stuff, it's easier to do. You can select things like Control Shift. It'll do select things. You can find and replace. That's all the magic stuff, but you don't really need to know that. Just a text editor with some magic stuff built in to help. Cool. Yeah, code linting is another one. Anyone familiar with that expression? If I say code linting, it's basically like, it won't find bugs, but it'll find ugly code. So like if you've written a one-line function that's like 400 characters long, it'll go, hey, maybe you should break that. So like it'll give you limits. It's a good thing to put some linter on your code, then you won't end up with really ugly code. It does actually catch bugs because it's usually when you've written something trash and it will remind you like that looks bad. So it isn't bad, but it looks bad. So you should probably do that. Same as like style for variables and functions and naming. Cool.
Is it just for the aesthetic or does it capture like, oh, it's missing a semicolon? Or like
it depends on the language integration. Usually a linter's pretty dumb, but they're getting better. Lots of this stuff will, like, usually if you have the plugin for the correct language, it'll help or not, depending on how mature the language is. Julia is one of these weirdy ones that's a bit new, so not going to be as good as if you're in Python or TypeScript or JavaScript or something. Cool. Okay, software licensing. I should say this because I got out into the world and I didn't know how it worked, and that's kind of embarrassing. But when you're in a commercial context, it matters. I'm not a lawyer, so this is going to be like rough field guide, I think I said, because it's like, there's these things, I should say what they are. I'm not going to give you legal advice about how to use it. It's kind of up to you, but there's a vast class of stuff going with software, and there's two broad classes. There's the world I live in, which is proprietary software, where it's super secret. Nobody gets to see it, who's not me, like inside the company. Even inside our company, we have restrictions on who gets to see the super secret stuff. Not everyone can see all the source code, which is a problem, I think. And then you've got free and open source, which is kind of the other big camp, which is kind of surprising it exists when you come into this world. There's like lots of people, lots of really smart people have released stuff into the wild for free and you get to use it. So Julia language included. Yeah, this is like, so if you ever get your hands on proprietary software, which does happen, people will release it on the internet. So if you just go into Google and start searching for stuff, you should probably check the provenance. There'll be a license file included or not, and be a bit careful if it doesn't have one. Because proprietary software is a closely guarded secret and lawyers will come after you if you use it to make money, usually. If you're not using it, if it's like in a uni assignment, nobody will care. But if it's for, I shouldn't say that, don't do it. But yeah, if it's in a commercial environment, you're in trouble. Like, that's like, there's been multi-billion-dollar lawsuits on this stuff. Like, it's crazy, usually between big companies. Yeah, now this one is, there's classes within open source as well. That doesn't mean you can use it however you want. There is a class for that, but they're not all like that. It doesn't mean you can do whatever you want. And mostly I would think about this at your level as like respect for the person who made the thing. They had an intention about how it should be used, and you should respect that, like, because they're a person, they're a real person who made this stuff. It's actually kind of surprising how small the field is when you come into it. Like, there's not that many people working on open source. So you can actually get to know a lot of these people. Like if you go on GitHub and you start working on a project, it's a small pool. Three broad classes. Permissive license is the one that's your friend if you're going to go into business. Like this is, in my world, I'm happy to use this stuff. Everything else is a bit of a worry. Permissive means you can use it as long as you have attribution. The license classes are BSD, MIT, Apache. Copyleft is a really interesting one because this is like a, I guess, a strong ideological stance that they wanted open source to be viral. So like if they write this and you include it, your code becomes GPL as well. It's kind of a weird system. So it's like the idea is this is a viral license. So they wanted it, everyone's open source to be free for everyone forever. And this is a mechanism to drive that. So kind of interesting, kind of annoying because it infects your code base if you're not careful. So like you can accidentally include one of these things, not even knowing, you know, it's as easy as you get into Julia and you go using some random package, I don't know, AMQP or something. Oh, AM. Got that the wrong way. So, you know, there's, oh, I don't know. I'll pick a random one. I think that one's, I think I'm getting the name wrong, but there's a million packages in Julia. You include one, you don't check the license. That's in your code base now if you're linking against that. So be careful. Most of, if you go to GitHub, you'll see most, what can I do? Let's see if I go, let's go here. Down here, you'll see a license file. It'll be one of these things that will ask you when you go to create a repo in GitHub, there's automation around this stuff about including a license. I would recommend just including the MIT one. Depends on you. This is one I did years ago, 2015. Under this one, most of these things will have a license file. If they don't have one, be a little bit suspicious. But there's a thing called transitive dependencies where this thing might depend on other things and those things will have licenses too. So you can imagine it gets really complicated really quickly to track this stuff. Doesn't mean it's bad. There's famous cases. I think it was a famous car company. Someone found out their infotainment system had GPL code in it and they went, hey, big car company, I want your source code. And so it's on GitHub now because they got it off them. They got it on a DVD like 6 months later. So I think it was something like QT or something is GPL. Examples of this stuff, so you know, proprietary would be the big evil Microsoft, Windows. Mac OS is proprietary and something like MATLAB is proprietary. You'll never see the source code for those things. Permissive ones, examples would be Julia, is MIT. Python's got this Python-specific license. They come up with their own. Android is a weird mixed one because it's Apache for the user space and GPL for the kernel. That's a separation that happens. So the kernel bits comes from Linux. So it's kind of inherited it from there. Copyleft is Linux itself. So your program can run on Linux. Doesn't mean it's GPL because there's kind of this separation that's a little bit lawyerly and arbitrary. And there's also public domain, which is kind of like, yeah, whatever. And examples of that would be BLAS and SQLite. They're just like, yeah, don't care. That is a thing that exists. BLAS is a numerical linear algebra library, so that lots of people use.
Effectively, public domain would be the same as permissive. Is
kind of a bit weirder than that. Yeah. Like there's kind of arguments like anything you get on Stack Overflow is probably actually public domain where it's covered by copyright and not by this license stuff. So I don't actually know. I'm out of my depth. Someone go consult a lawyer, but they're the classes. You'll see them. I'd just like rule of thumb is like big no for proprietary. If you ever get your hands on that, GPL, be careful in an academic context, whatever, just realize your stuff becomes GPL too. If you care, like if you go out and want to start a company afterwards, you go, oh, God, I have to rewrite everything again. Yeah, permissive is the way to go. That's pretty much go. And public domain's pretty much go as well. Okay, cool. That's pretty much that. Any questions on that before I move on back to the start? Everyone's happy? Okay, I'm happy. That was only 15 minutes. We're good. Okay. All the way back to the start. This is a long unit, so we're going to have to race through this guy in the next one to get through. Okay. So I hope everyone's really familiar with basic Julia syntax now. Everyone happy? Out of 10? Where are you? At 10 out of 10? Who's 10 out of 10? You're 10 out of 10? Yeah, cool. Who's 1 out of 10? Because you should come to the consultation that's now on Thursday. So if you're worried, come to that because we don't get too many people. Okay, I think I tried to lead here coming up to this section because this is a bit where I think maths people are really good at doing computer science stuff. This is like reasoning about complexity of algorithms and where you can make a huge difference. So I've had examples where I've managed to make things many hundreds of thousands of times faster. So there were things that would take days to run. I got down to minutes and I was really happy. And it's kind of a fun game to play as well. Question 6 is your guide. Has anyone started question 6 yet? Nobody's tried? Oh, you've tried? How are you going on the runtime so far?
It started well. Like I did something at the start and it was good, and now I'm stopped.
What sort of order of time are you getting for the runtime?
I haven't got 6 yet. 5 takes like 3 minutes.
Yeah. So just for reference, don't take this as like you have to do this to get a good mark. But Andy, who taught it last year, got it under a second or so for question 6. I was a bit over a second, so I was a bit angry at Andy, and I cheated really hard to get that time. So I do things we're not teaching you to try and make it fast. Okay, so it's a huge area. So I talked about it when I was talking about addition. So when I said the primary school algorithm for addition and multiplication, we kind of said, oh, it's linear for addition and it looks like it's quadratic for multiplication if you go through how many steps you have to do. It's kind of interesting scaling. And we're going to take a boring problem that every computer science class does, and we're doing it in this maths computer science class, programming class. I'm sorry, everyone, but everyone does sorting. Sorting is not interesting, I think, personally, because it's like I've never had to actually worry about it too much. A little bit for doing discrete event simulation that comes up, and that will come up later in this course, I think, for you guys, hopefully. But more about priority queues so much than sorting. So that's the kind of interesting application. We'll talk a little bit about that. So the reason we're doing it is because it's easy to understand. That's the main reason everyone teaches it. And the first algorithm we teach, it's a terrible algorithm and don't ever use it, but it's easy to reason about. So we've got this thing called bubble sort. Let's just go out of here. The data. We'll just do a small thing so we can see. Really common thing is you want to go, I want to sort this thing from biggest to smallest. Of course, there's going to be a built-in function. Sort data. You could probably guess the name too. And it will be in every programming language. Again, you want to see how this thing works. There's a bunch of different things. So actually a lot of keyword arguments here that are kind of interesting, right? Because you can choose the algorithm, which is not normal for most of these things, if you want to. There's this funny is less thing and a by thing, and you can change the direction. So, if you want to go, you can sort from biggest to smallest or smallest to biggest. Cool, useful. How does it work? Anyone want to guess how to sort an array if he hasn't done it in a previous course? What's a naive thing you could try? Keep it. Yep, that's right. That's pretty much it. So the dumbest thing you could think of that's not pathological, I would say, is this thing called bubble sort. It's got a bit of a silly name, and I'll show you an animation maybe if I can find one quickly. Yeah, implementation of this is really simple. We'll just go through it. I think it's worth laboring on it because we want to see. Okay. So, have you come across this syntax before for functions with the exclamation mark? Has that come up? Does anyone remember what it means?
You're gonna change. Was it a global variable? No, something like that. No.
It's a hint to the user that you're going to do something annoying and mutate the input. So it means I'm going to take A and I'm going to rearrange it. It's just a convention though. I can totally remove that exclamation mark and nothing changes. It's a hint to the person calling that this is going to mutate your input. You can easily set up things that don't mutate and pretend it does and lie, or the other way around and put the exclamation mark there. So I kind of don't like it as syntax, but it's just a convention in Julia that if you're mutating your input, please put an exclamation mark there. Okay, so example of this might be pop data gets off the first thing in the list. So I'll just show you what data is before I do this so it's not so confusing. This should take off this last element in the array. And if I look at data now, that guy's gone. So if I keep going, pop, 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 pop. I wish I hadn't done 10. Yeah, so now data is empty because it's taken away to nothing. So this is a hint though. It's nothing forced in the language syntactically to tell you that it's mutating. Everyone happy? Okay, let's go through this function then. So what we're going to do is we're going to get the length of the array. We take in A. We're going to go swoop through the array in waves. We're going to go from the first element to the last -1. And then we're going to go again through the array. And if we find two elements that are one's bigger than the other, we're going to swap their places. So if you're going through, if one's bigger than the other, if the array's already sorted, what you're going to do is you're going to go through and you're going to go like, oh, this is less than this is less than this. You're going to swoop through and do nothing, right? So bubble sort's kind of cool. If the array's already sorted, it doesn't do anything, which isn't the case with other sorting algorithms. But if you find any two elements that are out of order, it will swap their places. Happy with that? Everyone can kind of understand that? What's the complexity of this algorithm by just eyeball? N squared? Why is that? Order N squared. But
Okay.
yeah, because it's got two loops. Yeah.
Two loops.
Mm. Yeah, that's right. So not rigorous, but we're just going to look at it and go like, oh yeah, it's going from I to n-1 and j is going to go from n-1 and it swoops through. The reason it's called bubble sort, I'll see if I can find an animation, but let's just show it works actually. Oh, data was empty. So that's cool. It works if there's nothing in there. That's a good edge case. So we've got this thing. We're going to bubble sort data. We look at data. Data is sorted from smallest to largest. Cool. That seems like it worked. Let's see if Wikipedia is cool and it's got the animation I wanted to show. It's got this, like, this is basically doing the comparison where if you find two out of order, swap them, move across. If they're out of order, leave them, then swap, swap, swap. So the reason it's called bubble sort is because the biggest values kind of float up to the top. That's the stupid metaphor for why this algorithm is called bubble sort. I hate the name. Doesn't make sense to me, but here, this is the one I want to see. If you have a thing where we're going to go iterations of this thing and how it goes through, you can kind of go, it's floating up to the top. That's where the weird name comes from, bubble sort. Okay. Yeah, so key question is how fast does it run? How much memory does it use? So as I was saying the other day, I said I showed you top and I showed you like I sit there watching the CPU and the memory, making sure I haven't written a stupid algorithm, getting ready to kill it just in time. Yeah, these two are huge questions. And how fast does it run? It's like massive question, especially in this day and age of like, I think LLMs are offensively inefficient at the moment. So if you want to go and make a big difference in the world, go and make training for LLMs work in a reasonable amount of time on neural networks. That's insane. So I think I heard 3 months for GTP4 on several thousand GPU servers, if that makes sense. So 3 months, and I think you can calculate the electricity, and most of the training was electricity, and it's in the order of tens of millions of dollars in electricity for training one of these things. So runtime matters. Memory matters in a way of like go, no go, because if you don't have enough memory to run it, you can't do it at all. That's kind of where that comes in. And you often can trade these two. You can trade speed for space and all sorts of other things. Yeah, huge thing, and we need to get better at it. Cool. I would recommend this thing. Anyone aware of this guy? Has anyone used benchmark tools before? Does it come up? No? When you, what's that? Yeah, so like it's more, there's a funny thing with Julia, and you probably would have noticed this. The first time you run a function due to pre-compilation, it's slow, and on the second one, it's fast, blah, 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 blah. This is like, if you're going to be super fussy about timing, you have this macro B time. So it might take a bit of time to run this one. I'll just show you this for when you're actually doing real work. Benchmark tools will give you a bit more information about like how long it actually takes to run. If you're lazy, you can just do time though. You'll actually rerun it multiple times. Once you press that up so we can see the timing stuff. You want to see something like if I run it equals 1 to 100 times. You know, if you want to get accurate timing, it can be a little bit fussy. So B time will automate all that stuff for you with the startup time. Much more useful. In the notes, we've just been lazy and we're using time all over the place. Sorry. A little bit of interpretation required about what's slow, and we'll talk about this later as well. This is the time it took to run the thing, and this is a hint about what might be going wrong because memory allocation tends to be the slow thing. That's the thing. That's trick. Anyway, I think I've lost the thread. So we've got this really bad function do timing here, where we're just going to make data, run bubble sort, time it, do it again on small data, compare it to built-in sort, then we'll do a big one. So what the difference is here, we'll do it on like a tiny array and then do it on a big array, 10 to the 4 elements for rand. You see the timings here. So on small data, bubble sort and the like down in the microns, like microseconds, they're really slow. They're really quick. So too quick to actually capture in this. But you'll see once you get to bigger data, this guy's growing way worse than this time. Runtime's getting 0.1 of a second compared to 1,000th of a second, basically. So bubble sort is empirically way less efficient than the built-in sort. So now there's things you can do to cheat, and I think this is funny because Julia's finally caught up with the notes. Has anyone read through this bit yet or not? It's actually funny. So what we're doing here is we're showing you a naughty trick where this inbounds macro. So what this will do, this is again, I was saying I was cheating when I was trying question 6 when we were benchmarking it. So inbounds. So what this will do will eliminate array bounds checking within expressions. So I'm doing, if I've got an array data, if I go data 1 and data 10, that's cool. That's the size array. If I try and do something silly like data 11, it'll go, bounds error. You can turn that off if you're brave, and it will read a random bit of memory or crash the program or something. And that's what this inbounds macro does. So if you're guaranteed this thing's going to stay inside the bounds, you can turn off that check and it goes a little bit faster. What's that?
If you're not testing it.
Let's
You're
see.
turning off the test.
Yeah. Oh, no, I can't. Oh, I can't do a single line demo, but you could try indexing off the array and see what happens. It'll probably crash my Julia session. It's fine. But if you're like super, super sure, you know, like I set n here, I can look at this all day and I'm going like, it is not going outside this array bounds. I can turn off the bounds checking. And then it will go maybe a little bit faster. And funny thing is, if we look at the logging here, bubble sort is faster than slightly faster bubble sort. I think that's probably just the imprecision in timing, because like whenever I run this timing, what actually happens in this time macro is it will poll what's happening and take a snapshot of it. If there's other programs running and whatever's going on your computer at the same time, it can make that confusing about what's going on. I showed you this thing top yesterday. You'll see on my computer, I've got, you know, Zoom's thrashing, there's some GNOME thing going on, there's some Pulse audio thing going on, blah, 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 blah. In my CPU, Julia is not the only thing running, and they might fight a bit for resources because They're just pretending, that it's a that this thing can do lots of things at the same time. Down at the low level, it's kind of has to fight for resources. So that's what the B time macro is for, to give you much more accurate timing. But again, this is like firmly in the realm of dirty software engineering tricks. It's like, we're really more interested in this course in like algorithmic tricks. Like they're the ones where you really win. That's how you get much, 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 much faster. So this is kind of like, I put in the count, the trick of this is like, you can do things in parallel on threads. That's another thing you can do. And sorting threaded is probably really complicated. I don't want to think about that, but basically the computer can, you can use all the cores on your CPU to do things in parallel. That's a way of making things much, much faster, with consequences and very, very exotic bugs, I would say. So be a bit careful about doing that. It's not a beginner move to start working with threading. Okay, but it didn't even work. That's the funniest thing. In older versions of Julia, I think if I go back to the notes, what was the first year we did this? 22. I'll just pick a random year. This isn't unit 3 back in this year. Yeah, you can see it used to be faster. But Julia got better under our feet. So that's kind of funny. I actually like that. Yeah, ideally that inbounds macro wouldn't exist, I would say, because it's kind of a terrible thing to do and will just cause a really exotic bug. Okay, this is where, empirical things, like often it's really hard to reason about this stuff. Like we'll give you the easy example and you can kind of look at it and go, okay, oh yeah, there's 2 for loops, it's quadratic. Can get really hard to reason about this stuff. So empirical testing of this stuff is a thing I do commonly, like how things scale. I go like, there's a quadratic bit there and there's a squared bit there, but I don't know which one's actually going to be dominant for the data size I'm working with. So empirical testing is really important. Here's an example. I don't know if there's much interesting in the syntax. This one's probably interesting. Has anyone seen, if I have this, anyone going to guess what that's going to do if I run that thing? That's right. So much easier to just go. So if you want an empty array, you can do it that way. You can also do it this other way. If you actually know the size of it though, if you're not going to push things in, I can make this is just random initialization. I said like you're just going to read a random bit of memory or some odd thing's going to happen. You can do this undef if you know the size. But if you don't know the size, you can do this. Or if you like confusing students, you can do that too. But good to see it. So you've seen the syntax. I told you about pop. Pop's best friend is push. It's the other way. So if I've got like push times 1 times now, it's because it's mutating underneath my feet, times now has 1 in it. If I want to push 2 in, sorry, 2, it comes on the bottom every time. So that's push. And then if you want to undo it, they're kind of symmetric. Oh, sorry, you don't give it a thing you want to pop. I can go back to, hopefully, times is empty. Now, cool, push and pop, useful things. I think that's the only thing interesting in there. Timing is usually a bit of a pain. You can call this function time nanoseconds, and it will give you the current time in nanoseconds from GPS epoch, sorry, from Unix epoch. So since the 1970s, they've started counting up or something. I don't know what the time is from. Give time in nanoseconds. So this, yeah, okay, cool. No, it doesn't, it's not from epoch. It's just a kind of a random 0 for the start time. But you get the current time in nanoseconds and it wraps every 5.8 years. Why would it wrap every 5.8 years? What's that? Yeah, 64-bit. So that's right. So it's just this uint thing again. So it's a uint 64, and there's going to be like 2 to the 64 minus 1 of those. So to calculate how many nanoseconds is 2 to the 64, it's 5.8 years. That seems like not long, maybe for I don't know, 2 to the 64 minus 1 nanoseconds. It's like a really small thing and a really big thing fighting each other. Yeah, so if you want to do timing and you're not going to take more than 5.8 years, you can use this and you can just subtract them if you want to see what's happening in between. So what we're doing, it's probably easier to just capture that at time macro, but there's, there's a million ways to do these things. This is one way to do it. We'll do the start time. What we're going to do is we're going to go through the data. This is a bit silly. I wouldn't do this. Who sees, I guess you guys are getting more sophisticated. Can you think of a better way to write that code? I don't actually like it. It annoys me if I look at it. So in this swing, we're slicing this array from 1 to n, and we're going from n in this range. So it's going to go in steps of 500 up to 10 to the 4. It's going to generate all the data, and then it's going to bubble sort this thing up to n. What would be a better thing to do there? Yeah. Either outside the loop, you'd go move this guy outside the loop back here. That's a really good thing. And then you're always using the same data. If you don't care so much about the data, I'd probably just generate only up to, that's kind of weird. You shouldn't actually need to do that slicing as well, because you're only generating up to n. There's a couple of weird things going on there. So
If you want a different direction, you just generate a massive listing and take slices.
Yep. Yeah, these are the kind of, that's exactly right. So these are the kind of tricks you're doing when you go to these questions. You're trying to make it fast. Think about things you can only do once, right? And then just do them up front and then never calculate them again. Try and do the fewest number of calculations, or in sorting's case, try and do the fewest number of sorts you can. That's going to be like always in the back of your mind if you're trying to come up with how to do these things. That's what you should be doing. Like never try and do something twice if you don't have to. Because it's in nanoseconds, it's going to convert it to milliseconds, and we're going to push that onto this times array. Everyone happy with the code? You can understand it? Cool. Empirical plot, I could reproduce this. I don't know if I will. Let's do it. See how long it takes. Didn't take that long to actually run. We'll see if on my computer we get the same thing. Bit more of a squiggly line, because this thing is like this timing is fairly non-deterministic on an actual computer. There's other stuff going on. Other things will start to win, like allocation. Like if we're actually generating these random numbers, maybe that starts to get slower than the sorting, and we'll actually start timing that. It all gets a little bit confusing. Cool. Okay, we said we thought it was quadratic. It kind of looks quadratic. Who's a real statistician and can tell me how would you prove it was quadratic from data? Sorry? Oh, anyone? You can all have a go.
Something like of it, and then I do.
Yeah, logarithm, and it's like engineering style. Look at the slope and see if the slope is 2. That's kind of the thing you would do. It's actually, I would say model selection is like the last, like model complexity selection is like the last great frontier in statistics. It's like, how do you actually robustly prove something like that is actually really hard. But engineer plot, log plot with a fat texture, everything looks linear, that's fine. Yeah. Yep. And see if the slope, see what the slope is, and then you get some empirical idea of the order. Yeah. So like that's actually kind of like the sophisticated ways to do that with regularization, something called regularization, where you're going to go, I want to, like, if I took one of these points away, how sensitive is my fit to that order? And then you can do tricks like that to see if that, helps you choose the actual correct order. We got like a really dirty one. This is like politician version of proving that, where we're going to go, if it was quadratic, we'll fit a linear model to it and see if the residual is small. And it's like, what's the lie of doing this method, I guess? What would be the problem? Yeah. What will happen if I increase the model order? That's my question. Like if I put to the 4th or to the 99th, like you were saying, the residuals will keep getting smaller as I go bigger, because it will just fit the data better and better as it becomes overdetermined. So this is kind of a lie, but we'll do it anyway. This is like useful for seeing this GLM package. Has anyone seen, this would be useful for statisticians. Don't think I've added it, but you can set up, it's kind of like a nice thing. You can set up a linear model with a formula and fit it to the data. It will give you nice statistics, everything you'd want. There's a data frame here. Has data frames come up in homework yet? Anyone had a wrestle with that? Everyone, the Python equivalent is pandas. Is everyone familiar with that? But basically this tabular data, like we'll talk more about that later in the course, but this is a thing. I think there was a question on the Ed forum thing about this going wrong for a symbol, but usually you wouldn't set it up like that. That's kind of confusing. Usually you'd go like data frame. Oh, did it? I just added GLM. I didn't add data frames, did I? Sorry. Yeah, it's this idea of tabular data, like a column, like an Excel sheet or something. Data frame's a nice data model for this and gives you lots of useful things. I don't think there's much else to say. You could see this stuff, you'll get your residual statistics, and so looks like small residual. So, and if you plot a thing through it, it looks like it fits. So that's a bad thing. I think we did the old, yeah, so this would be more compelling argument if you go like, cool, we've fit a model, let's be like scientists and go like, how well does it predict somewhere outside the range? So that's what's going on in this little bit of code. It's predicting and it goes like, well, the predicted time was 0.9 seconds, and the actual time was 1 second, predicted time was 2.4, actual time was 3. It's actually not bad for this sort of thing. It's like growing quadratically, but the error should grow quadratically outside the range. Yeah, this is your one you were saying, if you just plot it on a log plot and look at the slope, that's another way you could do it. Cool. So cool, looks empirically with some dirty stuff. It's actually kind of like when you're getting in towards, if any of you go into machine learning or advanced statistics, this model selection thing is the biggest problem. It's like, I guess I spend a lot of time on neural networks, and doing architecture search is a big deal. It's like some version of this model works and some don't, and it's not clear why, and you have to do search over models to get something that actually works. Yeah, so this thing where I've said it out loud, but big O notation is a thing to know. You know, you get it in mathematics, but like classifying, when people talk about it, they tend to talk about, you know, there tends to be classes. It's like scales like a log, scales linearly, scales n log n, scales like n2, n to the 3, blah, 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 blah. Worst case is 2 to the n. So who's got really good intuition and can say why 2 to the n would be like something you would see? What's that equivalent to? Yeah. So like if you go think of it like set theory, this is the way I do it. I've got a set coming in. What's the cardinality of the power set, right? So I have to check every version of those through the thing to see which one's the good one. Yep. Big class of actual algorithms do scale like this. So believe it or not, there'll be companies in Brisbane who do consulting, doing mixed integer linear programming. Anyone heard of that? Anyone doing operations research? Maybe some of you will, but traveling salesman problem would be the one. Is everyone familiar with that? Anyone got a description? Basically, like if you have a bunch of cities and you've got to go, I can only visit each city once and I've got to go around. What's the shortest path for doing all those? That's one that has one of these pathological scalings. But as you can understand, really important practical problem. So I think I said AWS, Amazon Web Services. Is anyone familiar with that? Some people not. That's basically renting a computer on the cloud. So like the idea came from Amazon had spare capacity for their computers. I think this is a bit of a lie, but it's a good bit of propaganda. They use all their computers at Christmas and not for the rest of the year. And someone had the bright idea of we should rent our computers for the rest of the year because they're just sitting there as reserve capacity. And they ended up making more money from that than from the selling the stuff. So that's a huge business that Amazon does. Renting computers. There's other cloud providers, Google do it, Azure. I have friends who work at Amazon, and I think in Australia, the airline routing is the biggest use of the computers, like working out this traveling salesman problem of like, it's actually a really nasty version of the traveling salesman problem because you go like, got to send a plane from here to here. This is how many people I think are going to be there. How much petrol am I going to use? Which one should I route? What sort of things should I put there? That's a whole big thing in industry, operations research. Huge use of computers for doing that stuff. So these really pathological exponential scaling ones are important. So ours is our n squared though. It's not the full story. Anyone got any intuition why it might not be the full story? Like the order, it matters, but in some cases it actually doesn't matter. I'd say, oh yeah. There's things like that, yeah. I had trying to aim at another thing though, yeah.
And presentation is asymptotic, so
Yeah.
it really cares about big inputs.
Yes.
So whenever you have a cap on how big you care about, the constants that O of n ignores start to become a lot more important.
That's exactly right. So that's the one I was angling at. So for example, when we were saying about the primary school multiplication algorithm being n squared, if you're only doing 64-bit floats, maybe you don't care. Like maybe that circuit depth is big enough and it doesn't matter. You can just get away with the squared one. But if you're going to big ints, then it really matters what the exponential scaling is like, the asymptotic scaling is like, because then that starts to dominate. So I said that algorithm, Karatsuba's algorithm for multiplication, if any of you want to go and look it up about how it works, that's n log n scaling, not n squared scaling. Another one that's kind of surprising, I would guess, is matrix multiplication. So naively, what would you expect? Like you've all been taught how to do matrix multiplication, I hope, by second year. Yeah. What do you think the scaling for matrix multiplication is? You're going to go this one times this one, plus this one times this one, plus this one, and go through and go through and go through. We'll say it's a square, but just to be clear, we'll say it's a square matrix size n for one side. What do we think it's going to be for that one you learn, like maybe high school, first year uni, like doing matrix multiplication? What would that be? N to the 3. N to the 3. The one that gets implemented on a computer, what do you think it is? I want to guess. N to the 2? N to the 2 would just be reading everyone once. So that would be awesome if it was. Not quite either. It's like n to the 2.4 something. And for the reason you're saying, there's actually better algorithms than that, but they don't use them on computers because the way they've implemented the one that they use, I think it's called Winograd's algorithm, is much faster on a CPU. Yeah. So kind of surprising. I don't think there's much more I want to say about that. So again, practical details matter. So like, can't get away from the hardware and you can't get away from dirty software engineering tricks. Like the actual way these things tend to be implemented on CPUs actually can dominate in some cases as well. So that's the example of matrix multiplication. Yeah, so we're just going to be loose though. I'm not going to we're not doing an algorithms course and I'll just get it wrong if I talk to you about this. Just keep these in your mind about what it is. So your intuition's perfect. Is like, why would it be n squared? Is we're going to go, we've got this for loop here, we've got this for loop here. We have a comparison and then we have this position swap. Which bit's going to be the slow bit in those steps 1, 2, 3, and 4 as well? The slow. Which one is the rate limiting step? Would anyone have a guess at what's actually slow?
I'm attributing the values.
Accessing the values? Is that what you mean? Like going... Oh, this one where they're swapping the memory. This one's actually fast. It's actually this comparison bit that's slow. I think if you do the timing, prove me wrong though. You can, I'll be actually wrong here. This is one where it'd be cool if you guys go off and try and time this and figure it out. Like which step in this is actually the slow step?
Because attributing a value to a place in memory, there's no method that.
You can just swap pointers, yeah. But the comparison bit, I think, is the slow bit. Yeah, so if you want to be careful and count them up, you're going to go outside loop runs n to -1 times. So if you want to calculate that, you get something like half n squared minus n1. The order, the dominating term as you get big into asymptotics is going to be n squared. That's what we mean when we're saying the order. So don't care so much about this coefficient. This bit dies as n gets big. That's n squared. what we're going to do here, this is this kind of dirty trick you always do in these courses, is we're going to put a counter in here and we're going to increment it and we're going to see how many times it counts and check that it equals the size. So as well just run that because we're here. And we'll go done. Just copy it all across. Hopefully this is true. So this will return K. So back here, I didn't really talk about it, I just said it. We've got a counter that starts at 0. Every time we do one of these comparison steps, we're going to increment the counter and we're going to return K. We're not going to actually return the sorted array, so it's just a profiling function. It's kind of useless, but we should see that's 28. And if we do this calculation, that's 28. If you don't trust me, we'll make data bigger. What size? So you know I'm not cheating. No, I don't want to be here all day. So that's doing that many steps. N equals length data. I think there was a bracket there, wasn't there? No. So, you know, that's how our analysis is sound. It's not that hard to reason about this time. Again, bubble sort is a terrible algorithm though. It's like, should die in a fire. Never implement this. If you go for an interview and someone tells you to implement sorting, don't do it. Yep. Bogan sort. Oh, Bogan sort. A Bogan sort might be what I do. Yeah. Yeah. There's lots of like, if you look up sort analysis of sorting algorithms, lots of people have come up. Bogo sort is one where it's like, what's the most pathological sorting? It's basically guessing and checking, right? Like, guess a permutation and see if it worked. And what's yeah. Yep. So that's a thing. Although I would counter that with randomized algorithms are actually really sophisticated. So I will show you an example of that if we have enough time in one of the later lectures where randomly guessing is actually kind of beats the sophisticated method. So I can show you one of those. Yeah, might get it on the first go. This guy's got good best case performance though. So as I was saying, if this array is already sorted, you can put a Boolean in here and go like just one sweep through and I can go like, oh, it was sorted. I didn't have to do anything. Stop, return, nothing to do. It doesn't have to be n squared. So when we're talking about complexity, there's kind of like a best case, worst case, and average case complexity. Depending on the application, they can be more or less important. And we'll get into that more next week, I think. I think that's a good place to stop. Everyone happy? Cool.